to switch on the recording. So let's now finish this. Let's find the equation of motion. What is the method? Summation of forces in the x direction is equal to mx double dot. And you can say that P is towards the right, right is positive, minus K. So please remember that they need to tell you where is your x defined as. This is my x minus K multiplied by x minus 0, because you have to make a free body diagram before doing anything. So what is my free body diagram for equation of motion? This means that my spring force is towards left, my damping force or damper force is towards left, my applied force is towards right, my weight is acting downwards, and the normal force is acting upward. But unfortunately I have made two wheels, but I have done this, these are massless, so don't get confused. My whole point was that there is no friction, so forget about being worried about that. You can make actually a normal force like this, or if you are getting confused, oh come on, then I can just remove the two little fellows. Okay. Oh, life is not good right now. Okay, and I can just, okay, and I can just say this is frictionless. Okay, the contact is frictionless, whatever. Now P minus, why minus? Because it's towards the left. Spring force is K into this point is X. What is this point, Mirch? This point has zero displacement, right? Similarly, the damper, you can call it by C or B, whatever. This point will have velocity x dot. What will be the velocity of this point? 0, right? Is equal to mx double dot. So in your physics classes, they taught you, right? Mx double dot plus cx dot plus kx equal to, done. This is what is known as equation of motion. Mx double dot plus bx dot plus kx is equal to P. What is this? This is equation of motion. How many initial conditions they require from you? 2, right? So you have to give some sort of initial condition. Let's say for this problem, 0.5 centimeters to the right. And the second initial condition is an initial velocity of -1 centimeter per second. Is this clear? You have to provide, this is the initial condition, and the applied force you already know. Fine. Continue. So next time someone says, give me the equation of motion for this, you can get a little confused. You did not give us the value of the mass. You did not give us the value of K. You did not give us the damping coefficient. What on earth do you even mean by equation of motion? Well, this is what I mean by equation of motion, right? That one equation that can talk about the dynamics of the system. Now, if let's say I want to have the equation of motion for this one, let me go to the next slide. Why don't you tell me the equation of motion for this one quickly? This is spring, okay, and this is damper. Okay, why don't you tell me the equation of motion for this one?
What is this damper?
Sorry?
What is this damper?
This is a viscous damper. Do you want me to explain to you the meaning of damper? Okay. So, for example, how a car, again, very conventional old car damper works. You have those 4 shock absorbers in your car, right? You have this spring that you usually see, and there is what is known as a damper. I'm talking about a very old viscous oil damper. How that oil damper works is you usually have this little disc inside you can have 1 or 2 holes, and there is oil filled here, right? So the moment you have a jump, that whole oil wants to flow through those little 1 or 2 holes and want to come in the upper compartment. So what happens is when this disc wants to go down, thick oil wants to go up. Now you have a spring, right? So this thing wants to now go down. Now it wants to go up, then it wants to go down, then it wants to go up. So you have thick oil that wants to go down, then it wants to go up, then wants to go down, and then wants to go up. That creates a damping force. So this damper, I'm using it here. Okay, give me the equation of motion for this one quickly. So this is my X. This is K. This is B. Anyone? What is the equation of motion? I'm not going to do this whole thing again. Frictionless surface. Give me the equation of motion. Summation of forces in the X direction is equal to mx double dot minus K into X minus 0 minus, because the damping force is towards the left and damping force is dependent on the velocity, is equal to mx double dot. So what is the final equation? Mx double dot plus bx dot plus kx is equal to 0. Okay, now tell me, is there any applied force here? Yes, no? No. So now tell me how this system will move. Any student? Let's say this is the initial condition. What is the meaning of this initial condition?
Over X. And the velocity and
Sorry. Okay, sorry. Yes, sorry.
Now it's moving flat. So
Okay, hang on. So this was the system. Initial condition means 0.5 by 100. I took the mass, stretched it 0.5 by 100 to the right. Then it says -1 by 100 meter per second, and I give it an initial push or velocity of -1 by 100. So what will happen? It will go 10, 10, 10, 10, 10, 10, 10, 10, 10. It will stop, right? There is a damper as well. My question is, if there is no applied force, then why is the system moving? Because of the initial condition. Okay, so a lot of these things you will study in the last part of 301. I'm just giving you a brief introduction. So why don't you just tell me a very simple thing? If I give 0 initial condition, x at time 0, 0, and x dot at time 0, 0, then what will happen to the system? Huh? It will not move, right? It will just keep sitting there. You will keep watching it. It is sitting there. You have to give it an initial condition of 10, 10, 10, 10, 10, 10, 10, 10. Now this one, for example, depending on the kind of force, what will happen? It can 10, 10, 10, 10, 10, 10, 10 for the rest of its life, because you are applying a force. I don't know right now the kind of force you are applying. Okay, I think so far so good. Yeah.
I have a question about B. So we said that
Damping coefficient.
damper is a piston, right?
Right now it can be anything, but right now to explain his question, I'm using a viscous damper. It's a damping coefficient.
So, for example, when we pull it like this, the damper affecting in opposite direction.
Of course, and when the mass is going to the left, the damper will exert a force to the right. Same with the spring. Mass goes to the right, spring pulls to the left. Mass goes to the left, spring pushes to the right.
The job of that damper is make the screen, I guess, less spring, like less.
No. Let's not say that. The job of the damper is to subside the oscillations. So to put very simply, if I am driving in a car and I don't have, let's say, a damping system in the car, I only have the spring in a pothole, I will have a jerk and I will just keep on oscillating all the way to my home, let's say. It will just keep on oscillating, right? Because there is no damping. Of course, this is an exaggeration. It might stop after, I don't know, 45 seconds or 1 minute, but that will be pretty bizarre that we are just jumping around on the road because we don't have a damper. Huh? We want to minimize the oscillation vibration. Okay, so please understand that you will talk about all of this stuff in detail in 301. Yes. Mitch. That means I took it 0.5 by 100 to the right and I gave it a negative push. If your question is why didn't you give a positive push? Yeah, we can. I could also give it a positive 2 by 100 meter per second. In fact, if you don't like this, look at here. This is negative and this is also negative. This means I compressed it negative 0.5 by 100 and I also gave it a push to the left. If you don't like it, why don't you make a positive? What does this mean? You compressed it negative 0.5 by 100 and then you give it a push to the right. Oh, sorry, something happened in my head. Thing happened. Okay, it had a snap. Okay, gentlemen, anything else? Everything is fine. Okay, let's change this question one more time. Okay, this is something that sometimes can confuse students, but I am intentionally going over this so that you never get confused. Let's say I change the system like this, right? Now you're thinking that, wow, now the system has changed. But again, you will cover in detail in your future classes. I am just talking very briefly about it. Again, this is my, let's say, X. I'm sorry, not X. I mean, Nini, this is my X. I mean, this is my X. I apologize. Okay. Okay. Now tell me, what is the equation of motion? Summation forces in that direction is equal to mx double dot. Okay, make the free body diagram. Okay, I'm not going to do it. You know, spring force to the downward, damper downward, weight is also downward. Now, this is where it will become very confusing when I write this. Minus k into x minus 0 minus b into x dot minus 0. Why did I forget your name? What is your name? Mehmet Safa. Yes, Mehmet Safa. Mehmet, focus here. Look, this is equal to mx double dot. You see, did I write weight here? Right? I did not. So you might think that I have made a mistake, right? Where did I write the weight? Okay, so let me just explain in very simple terms, but in more like in a detailed way. You can discuss this in the future in 301. Very simple explanation. Why didn't I write mg? Well, the simple, very simplistic answer is that I haven't made any mistake. The only thing is that if I take this mass and I look at it, there is a spring and a damper, right? I just observe it. What will happen is that the mass wants to sink into the spring, right? Initially, you have put it there. So what will mass do? It will sink in, right? For sure. So technically, the spring that you are observing is not unstretched anymore because the mass has sunk in. Once it has sunk in, then I draw this line and then I define my x. That's why I'm getting this equation. The fact that the weight had already deflected the spring initially, which is known as the static deflection. It has already happened. Then I took my line, drew it. This is my x equal to 0. Now, if you stretch the mass, 10, 10, 10, 10, the fact that that mass sunk in initially, which is your static deflection, is the reason you had mg equal to whatever in the beginning. But it doesn't show up here in the equation of motion because I drew the line thinking that it has already sunk in, static deflection has happened. This is my x equal to 0. If there is a student who says, no, I don't like this. When I put the mass, I want to draw my x equal to 0. I want to draw my line there. And the fact that it also sinks in, my equation needs to account for that. Then your mg term will appear here as well. But in very simple English, very simple terms, that sinking in that happened initially, your weight is responsible for that. And that's why this equation of motion and what I was showing you before has no difference. Yes, Gorkan.
No, in that case, we can't compress anymore, right? If you consider weight is already.
No, it will get compressed. So for example, I put the mass, it has sunk in. Now I will go there. Now I will compress it more and 10, it will oscillate. So now what will be your x? What are the initial conditions, anyone? X bracket 0. Let's say I will answer Gorkan's question, negative 0.5 by 100. And let's say you also give initial velocity also in the negative direction. I'm intentionally doing it because you asked me that question. Okay, anyone who can tell me what will happen if I apply a force? What will happen if I apply a force as well? Anyone? If I apply a force, then what will happen? We will have, this is P, right? You will have a P and you will have a P. Agreed? So far, so good. So sky is the limit. You can just keep playing with it. Why don't you now tell me another case? What will be the equation of motion for this one? Let's see if we have any student who can tell us. Oh, come on. It's very straightforward, right? I'm sure all the students will be able to answer. Hassan, you agree with us, right? Everything is fine. So now I have a damper. It's very hard for me to sometimes draw drawings. Again, why am I taking so much time, by the way? Okay, tell me the equation of motion, anyone? Oh, why the damper is touching it? I'm sorry for that. It's just bad drawing. Anyways, so tell me the equation of motion. This is my x. Again, my x is defined in such a fashion that static deflection has already happened. Let's say this is B, this is K. Equation of motion. Let's say this angle is 30 degree. Mirj, you can help us with this one. Tell me the equation of motion. Usman or anyone can help me, please. I appreciate it. It is equal to mx double dot. Is there any applied force? No. So I will have only minus k x minus 0, right? Because it's like this. Minus c into x dot minus 0 is equal to mx double dot. What is the equation of motion? Is there any difference? No, right?
What about the weight, hocam?
C, I'm sorry, not CB. We are using B. Sorry,
What about the weight?
the same answer I told just few seconds back, no? My answer was that I just explained in the last that the mass you hung with the spring and you just leave it. What will happen? It will stretch it, right? Initially, it will stretch it. So it has already stretched it. The weight is responsible for stretching the spring. Done?
Can
None?
you show the diagram? Can you show me the diagram?
Yeah, we can. But right now, I'm not going to show it. I'm not showing it static deflection. You can. So for example, you can draw another line in front of it or behind it, whatever, and can say that is my y. And then you can write the same equation of motion, my double dot plus by dot plus ky, but then you will have mg term that will pop up. But it's the same thing. My point is, I hung it stretched, look, it stretched. Then I drew my line that this is my x equal to 0. The weight was responsible for stretching it or for compressing it for that matter, like the first problem, whatever. And now my equation of motion will be the same. The weight is responsible, or weight component is responsible for static deflection. Is the static deflection part clear? Because things like these will be covered in future. I'm just going over it. Okay, why don't you now tell me some, again, this is something that will help you a lot in your future. Write it here, Euler-Lagrange equations.
So even though it was angled, it doesn't matter.
No, it does matter. So it matters in the sense that now the spring, sorry, I hung it. So it's stretched, right? So it stretches a certain amount because the weight is acting at an angle. If I had hung it straight down, it would have stretched more. So static deflection, when the weight had hung straight from the roof, the static deflection would be more.
X will have two components. X will have two components.
What has two components?
X.
You mean that stretching that is happening? Yeah, but why do you want to think like that? You want to divide it into x axis and y axis. I don't want to do that. For me, hang on. I will explain. If I want to talk about the equation of motion, I have defined my x along this plane, right?
Oh no!
I defined my x. Look at the way I have defined my x. So it's mx double dot plus bx dot plus kx equal to 0. I am saying it again and again. Equation of motion talks about motion, right? 10, 10, 10, 10, 10. So when it comes to 10, 10, 10, 10, 10, the object will do 10, 10, 10, or the object will do 10, 10, 10, or the object will do 10. Every time this motion is similar same for all the cases. Static deflection is different. Okay, now equation of motion by Newton's law can be very tricky. So there is a very easy way. Come on, like, are you finding it easy? Probably you are, but if I make it very complicated, there is a limit to our imagination of doing summation of forces in the x, summation of forces in the y. Just imagine if I connect too many pieces. Just to confuse you a little bit. If I ask you, give me the equation of motion for this one. So you will say, oh, come on, it's so easy, right? Right? Easy. Now let me make it complicated. It's very hard, right? Now this is attached to this one. It's not easy. It's very complex motion route, right? It's very difficult. So again, such kind of complicated mechanism right now, you are not doing it. You are in 208. But life is very difficult. So you cannot just always use, the simple summation of forces and summation of moments. So what we will do is we will do what is known as Euler-Lagrange. We can use this instead of Newton's law. So this is the strategy. The formula is d by dt delta L by delta. So this is your variable, okay? Minus partial derivative. This is partial derivative equal to, so you will have non-conservative forces or external forces, or this is or, by the way, and L is equal to T minus V, and T is kinetic energy and V is potential energy. Okay, do it for me. For the same spring mass damper system, I'm coming to your desks, by the way, because I think I really would appreciate if everyone gets involved. Thank you. So let me make it like this so you do not get confused. Let's say this is my X, and let's say this is my and this is my damper. And this is, so this is the question for okay, now tell me what is the equation of motion. Again, this is frictionless, by the way. Let me make this very nice horizontal.
T is kinetic energy, right?
Yeah. Yes. Yes, Usman. Okay. So just tell me the kinetic energy. Ghazal and Mehmet Safa. Tell me the kinetic energy, Mehmet. It will be, this is mass, right? Half m x dot square, right? Okay. What about potential energy? Spring. This is K. This is damper. So it will be half. Tell me the formula quickly. K x square, right? Or that delta square, whatever. Okay. Now, what is the damping force? It is minus C x dot. Okay. Hang on. Let's change this problem a little bit. Let's say someone is also applying a nice, beautiful force. Okay. Oh, come on. What happened? Like this. Okay. What about any other outside force? Any student? It will be capital P, right? Let's say that is a function of time. Okay. Now tell me what is, let's go step by step. Okay. Don't get confused. What is delta L by delta X dot? Quickly. It will be delta by delta X dot into, agreed? Yes, no? Now I'm definitely coming to your desks. May I do it on a piece of paper quickly? Tell me, what is the derivative of this whole thing with respect to dou by dou X dot? It's very easy. Trust me. Good. No, nothing else.
Minus 0.
Minus 0. Look at here.
Oh, okay.
Are you getting my point? Everyone understood how he said, because it's partial derivative with respect to X dot, so automatically that term will vanish. Yes, Hussain and Ahmed and Mehmet, it's clear, right? Okay, then as everyone, I hope Gorkan also agrees, right?
Yes.
Okay, please stop me if anything is not correct. Okay, now why don't you tell me what is delta L by delta X? I'm sorry, dou L by dou X. Again, follow the same strategy. Now what will happen? Dou by dou X into half M X dot square minus half kx square. What will happen now? Minus kx. Agreed? Okay, good. Last but not least, let's use a nice green color. D by dt dou L by dou X dot. Why don't you tell me what is the answer for this one? Search for dou L by dou X dot. Take the time derivative. So it will be d by dt dou L by dou X dot is mx dot. It will become nice, very nice, right? You understood how he said that, because he took another time derivative.
Yeah,
Right?
it is excellent.
Okay, so now let's go back. Put everything in that big equation. D by dt dl by dx dot. What is that? Mx double dot minus dou L by dou X minus. What is dou L by dou X? Well, here it is. Yes, it is minus. So it is minus kx is equal to, what is the right hand term? Non-conservative forces or outside forces. Non-conservative forces is my damping force, right? Which is minus cx dot. Outside forces, capital P. So it is plus P. Okay, now tell me, did I get the same answer or not? Did I get the same answer or not? Mx double dot plus cx dot, no, not C, I think it was B, right? I'm sorry. B. I'm so used to in my life using C, but here in our university, mostly I have seen professors use B as for damping, but anyways. So I have to adjust. Oh, come on. I hope I didn't use C anywhere else. Okay. Okay. Plus Bx dot plus Kx equal to P bracket T. Did I get the same answer?
Yeah.
Usman, is clear, right?
Yeah.
It looks very complicated. Now you would say, oh, come on. Using Newton's law, it was 20-second job. This is so complicated. But just to give you a perspective.
It's like a grand sparse derivatives, and it will be somewhat easy.
Right? Because if you have a very complicated system, your system boils down to only 2 bits. Find the total kinetic energy, find the total potential energy, and start taking those derivatives. There is absolutely, where did I even make a free body diagram? Apart from having, of course, I had to use it because I need to have a clear idea that the damping will act in the opposite sense and the applied force will be.
Now I understand why we need to use the Lagrange partialities, but why are we why are we seeing you Euler-Lagrange?
Oh,
So that does Euler come
I think
from?
Euler is the name of the person to say these things. Look, have you ever in your life seen this system, mass, spring, and damper? I haven't seen it. Come on, how many in this complete room do you see a mass, spring, and a damper? We don't see a mass, spring, and damper. When would I in my life actually have a mass attached with a spring and a damper? The point is that we are trying to model systems. So if I have this marker and there's a cantilever beam, I attach it and I deflect the cantilever, and then it will oscillate. So actually for me, that stiffness provided by the cantilever beam, that stiffness that it is providing, that is K, let's say. We are modeling that as a spring here. The fact that when it will oscillate, this air around it will try to dampen it, the oscillations, and the fact that there will be friction force as well. I am modeling all of that, let's say in the form of a damper.
The air.
Let's, I'm just giving an example. The fact that I take a blower and I flow wind over it, because of that wind, that whole thing goes like brrrr. That wind force is the P now.
And also about derivation of the question. For the first one, the partial derivation L with respect to x dot.
The x is the variable. So in our system right now, I only have 1 degree of freedom. There is only x. If I had 2-3 different variables, then there would be x, then theta, then whatever, all the necessary variables will keep on coming. Ask me the question. I think your question was not complete.
While taking the derivative at the purple part and that part, I couldn't do the derivation.
What?
Yeah, I did, for example, the m times x dot. I did, but why we didn't say anything for the 1/2.
Because you are trying to take the partial derivative. Got the question. You are trying to take the partial derivative with respect to x dot. And half kxk doesn't have any x dot. So the partial derivative, that they taught us this rule that if you're trying to take the partial derivative, that then for any other variable, I think they taught us this thing.
It will be 0.
Boom, it will go. So is it clear?
It's clear.
Again, how many initial conditions would you need? 2 initial conditions. You know that drill. I'm just telling you how to derive the equation of motion. In our next 2-hour class, I will see if I can cover some more examples. I hope it's clear. Thank you so much, everyone. Bye-bye.